That's an alien life breakthrough. Scientists have detected alien life 124 light years away from Earth. Let's
Do you ever
deep dive.
find yourself just, staring up at the stars and wondering, are we alone?
It's one of humanity's oldest, biggest questions, isn't it?
Totally. And well, today we're doing a deep dive into some really intriguing new clues, things that might push us a bit closer to an answer.
That's right. We're looking at a discovery that's potentially groundbreaking. It involves finding some very, very interesting molecules on an exoplanet. It's called K2-18b.
K2-18b. Even the name sounds alien. And yeah, our sources are definitely buzzing about these recent findings. They suggest something pretty remarkable could be happening out there.
Mm-hmm.
So our mission today, let's unpack these clues, really try to understand what they might mean for, well, the whole search for life beyond Earth.
Okay, let's do it.
All right, let's jump right in. The big headline here, the thing causing all the excitement, is the detection of two specific molecules in K2-18b's atmosphere.
Yes, dimethyl sulfide, that's DMS, and also dimethyl disulfide, or DMDS.
DMS and DMDS. Okay, why is finding these two molecules such a big deal? Why are scientists getting so worked up about them?
Well, it's fascinating because here on Earth, these molecules are almost exclusively produced by life, specifically marine phytoplankton.
Phytoplankton, like tiny ocean plants.
Exactly. Those little guys are crucial. They produce a lot of the oxygen we breathe. So finding their chemical signatures, let's say, on another planet.
Immediately makes you think, could there be life there doing the same thing?
Precisely. On Earth, DMS is, well, it's essentially a biological waste product, a biological exhaust fume, if you like.
Huh, okay.
So finding it, especially in large amounts on another world, it strongly hints that maybe, just maybe, a similar kind of active biology is at work. It could, fundamentally change how we think about where life can even exist.
Wow, it's like finding a chemical postcard saying life might be happening over here.
Like so.
So give us the context. This planet, K2-18b, where is it? What's it like?
Okay, so K2-18b is about 124 light years away. Not exactly next door, but cosmically speaking, fairly close.
124 light years.
Yeah.
In the constellation Leo, I read.
That's right, Leo. And it orbits a red dwarf star. Crucially, it orbits within that star's habitable zone.
Ah, the Goldilocks zone. Not too hot, not too cold.
Exactly. It's the region where temperatures could, theoretically, allow liquid water to exist on the planet's surface.
And water, as we understand it, is pretty fundamental for life, right? It acts as a solvent. It's involved in so many biological processes.
Absolutely essential, based on life as we know it. And K2-18b, it's thought to be what we call a Hycene world.
Hycene. Okay, break that down. High for hydrogen.
You got it. And ocean for, well, ocean. The idea is these are planets likely covered in vast, deep water oceans, sitting beneath a thick atmosphere that's rich in hydrogen.
So not like Earth with continents and oceans, but more like a water world.
Potentially, yes. Imagine a planet dominated by water, maybe a global ocean, under this dense hydrogen sky. It's a very different potential environment for life compared to our rocky, oxygen-rich planet.
It really does paint a different picture. How big is this place?
It's quite a bit bigger than Earth,
Yeah.
about 2.6 times Earth's radius, and significantly more massive, something like 8.6 times Earth's mass. So it's a substantial world, sometimes called a sub-Neptune or mini-Neptune.
Okay. And we already knew something about its atmosphere before this, didn't we? Didn't the James Webb Telescope find other stuff?
Yes, that's important. Earlier JWST observations had already detected methane and carbon dioxide in its atmosphere.
Which are also molecules that can be linked to life.
They can be, yes. But crucially, methane and CO2 can also be produced by purely geological processes, non-biological ones.
Right. Volcanoes, that sort of thing.
Exactly. So while finding them was interesting, it wasn't definitive. That's why this detection of DMS and DMDS is so, well, compelling.
Because these molecules have a much stronger tie to biology, at least based on Earth.
That's the key distinction, yes. The link between DMS, especially, and life on Earth is very strong. Finding it on K2-18b is a much more direct, much more exciting hint.
Okay, now here's something that really jumped out at me. This planet's year. It's super short, isn't it?
Oh, yeah, incredibly
Yeah.
short. It whips around its star in just 33 Earth days.
33 days for a whole year. That's just wild. How does that even work with the habitable zone? Wouldn't it be really hot or tidally locked or...
Well, it orbits a red dwarf, which is cooler and dimmer than our sun, so it can be much closer and still be in the habitable zone. A short year definitely means a Very different kind of seasonal pattern, if any.
Right.
But having a potentially massive global ocean could act as a huge climate regulator, possibly evening out temperatures.
Ah, okay. That makes sense. But the most striking thing, the real kicker here, seems to be the amount of the stuff they found.
Absolutely. That's what really grabs your attention, the concentration.
Yeah, because on Earth, you said DMS is present, but it's like trace amounts, right?
Extremely tiny amounts. We measure it in parts per trillion or sometimes parts per billion in the atmosphere. Very, very low.
But on K2-18b, the signal suggests... What?
The initial analysis suggests concentrations potentially over 10 parts per million.
Parts per million compared to parts per billion or trillion.
Yeah.
That's thousands, maybe tens of thousands of times higher.
Exactly. It's a huge difference. It suggests that whatever process is producing DMS and DMDS on K2-18b is operating at a vastly higher rate than on Earth.
And that makes a biological source seem, well, more plausible, because it's hard to imagine geology producing that much.
That's the thinking, yes. It's a major piece of the puzzle pointing towards potential biological activity. It's harder, though not impossible perhaps, to explain such high concentrations through known abiotic or non-biological pathways.
Okay, so let's just quickly recap where we are. We've got this ocean world, K2-18b.
Yep, in the habitable zone of its star.
Atmosphere contains methane, CO2, fine. But now, potential detection of DMS and DMDS.
Molecules strongly linked to life on Earth.
And at concentrations way, way higher than here.
And all this observed using the James Webb Space Telescope.
Which is just incredible technology. How does that even work? How do you look at starlight and figure out what gases are on a planet 124 light years away? It sounds like science fiction.
It is pretty amazing, but the technique is well established now. It's called transmission spectroscopy.
Okay.
Imagine the planet passing in front of its star, from our point of view. A tiny fraction of the starlight filters through the planet's atmosphere on its way to us.
Ah, like a silhouette, but with light coming through the edges.
Exactly. And the molecules in that atmosphere absorb specific wavelengths, specific colors of that starlight. Each molecule has a unique fingerprint of colors it absorbs.
So by looking at which colors are missing from the starlight after it passes through the atmosphere?
We can identify which molecules are present. It's like analyzing a cosmic barcode. And JWST has different instruments, NAROS, NIRSpec, and MIRI was particularly important here, that are sensitive to different ranges of these wavelengths or colors, giving us a more complete picture. AMI, the mid-infrared instrument, was key for the DMS hints.
That makes sense. It's just astonishing analyzing light from that far away to decode an alien atmosphere. Pure science magic.
It really feels like it sometimes.
But science always comes with caveats, doesn't it?
Yeah.
The lead researcher, Professor Niku Madhusudan, he's urging caution, right? We're not shouting aliens from the rooftops just yet.
Absolutely not, and that's crucial. Professor Madhusudan and his team are being very clear. This is an intriguing detection, but it needs confirmation and further investigation.
So what's the main point of caution? Is it that maybe something else, something non-biological, could be making this DMS and DMDS?
And that's exactly the question they're tackling now. Could there be some unknown or unexpected geological or photochemical process happening on K2-18b, given its unique conditions, the hydrogen atmosphere, the ocean, the radiation from the star, that could produce these molecules at these levels?
Right, they have to rule out all the non-living possibilities.
Precisely. They need to model different scenarios, see if any known abiotic chemistry could fit the observations. That's the essential next step in the scientific process.
Okay. So it's a hot lid, maybe the hottest yet, but the detective work continues. And you mentioned the statistical significance. It's currently at 3 sigma. What does that mean for us non-statisticians?
So think of sigma as a measure of how confident scientists are that a signal isn't just random noise or a fluke. 3 sigma means there's only about a 0.3% chance the detection happened randomly.
Which sounds pretty low.
It is quite low, and it's generally considered evidence.
Yeah.
But in fields like particle physics and often in astronomy, especially for extraordinary claims, the gold standard for a discovery is 5 sigma.
And 5 sigma means the chance of it being a fluke is...
Much, much lower, something like 1 in 3.5 million. It makes the result incredibly robust.
Okay, so 3 sigma is, this looks really interesting, probably real. 5 sigma is, okay, we've definitely found something.
That's a good way to put it. So while 3 sigma for the DMS is very encouraging, it's not yet considered a definitive detection by the highest standards.
And getting to 5 sigma means more looking, more telescope time.
Yes, exactly. They estimate they'll need somewhere around 16 to 24 additional hours of observation time with JWST, focusing specifically on the wavelengths relevant to DMS to hopefully reach that 5 sigma confidence level.
Wow, telescope time is precious. That really shows how careful and thorough this process has to be.
It really does. Science is patient, meticulous work, especially when the stakes are this high.
But even with the caution, this feels significant, doesn't it, in the grand scheme of searching for life?
Oh, absolutely. Professor Matsudahan himself used the phrase pivotal moment, and I think that captures it well. Even as a potential detection needing confirmation, finding hints of biosignatures like DMS on a potentially habitable ocean world relatively nearby, that's huge.
It focuses the search, maybe. Tells us these Haitian worlds are really worth looking at closely.
Exactly. It validates the strategy of looking for these kinds of worlds and these kinds of biosignatures. It tells us we might be on the right track.
And it feels like there's momentum building generally, right? I remember hearing about complex organic molecules found on Mars recently, too.
Yes, different contexts, different type of target, but it all adds to this sense that we're developing the tools and techniques to find increasingly complex chemical signs related to life or its precursors beyond Earth.
It's like we're slowly assembling pieces of this enormous cosmic puzzle. Are we alone? Maybe we're getting closer to finding out.
Each discovery like this, even the tentative ones, refines our search and fuels the hope that we might find definitive answers someday.
Okay, so let's just pull this all together for everyone listening using the incredible James Webb Space Telescope.
Scientists have detected potential biosignatures, specifically dimethyl sulfide, DMS, and dimethyl disulfide, DMDS.
In the atmosphere of the exoplanet K2-18b, which is thought to be an ocean-covered Haitian world in its star's habitable zone.
These molecules, especially BMS, are strongly linked with life on Earth, particularly marine phytoplankton. And the amounts detected on K2-18b seem surprisingly high compared to Earth.
Which is really the intriguing part. But caution is key. More research is needed to rule out non-biological ways these molecules could be produced there.
Right. The current detection is at a 3 sigma confidence level, which is promising but not yet definitive. More JWST observations are planned to hopefully reach the 5 sigma gold standard.
But still, this discovery, using that transmission spectroscopy technique, represents a potentially major step in the search for extraterrestrial life. Professor Matsudahan called it possibly a pivotal moment.
And combined with other findings like organics on Mars, it really feels like the search is accelerating, pushing into new territory.
It's amazing. We're using our understanding of life here, tiny microbes in our oceans, to interpret faint signals of light from a planet trillions of miles away.
It connects the microscopic on Earth to the cosmic scale. It's pretty profound when you think about it.
It really is. Well, that wraps up our deep dive for today. And it definitely leaves us with something big to chew on, doesn't it? Just imagine a world out there, maybe K2-18b, maybe another one teeming with life, maybe just microbial life, maybe something stranger, but life that's fundamentally similar enough to produce chemicals we recognize, yet evolved in a completely different sea, under a different sun. What would confirming that really mean
Comment
for
your
how we
thoughts
see
on this
ourselves, our
story.
own planet, our place
Thanks.
in this vast universe? How would it change our definition of life itself?
Big questions.
Definitely big questions, questions that keep us looking up, keep us exploring. And thanks to discoveries like this one, tentative as it might be for now, the universe suddenly feels, well, maybe just a little less empty and a lot more full of possibility.